All right, what's up, guys? Thought I would go through and show you how to do another question from your homework. Feel like it would hopefully help you. I didn't think that we had enough, or at least as much time as I wanted to, going through ICE tables. So this is question 8 from your homework. The one over calculations involving equilibrium. So just like we talked about, first things first, let's rewrite our equation. And then, as always, we're going to come in here and we're going to set up our ICE table, right? So the way we set up an ICE table underneath our reaction is we just go ICE, and then I just prefer to do it down the line. Remember that I is just our initial concentrations or partial pressures if we're dealing with gases. C is change, so it's how much from our initial to equilibrium did we actually change in terms of concentrations or again partial pressures. Of course, E is just always equilibrium. Whatever we write here is what actually goes in the equilibrium expression. So putting it all together, we're going to fill out this table and hopefully be able to do some math. So you'll notice, and our goal here is calculate the equilibrium concentrations, okay? So that would mean this is your end goal in mind. You want the actual numbers of those in that table. I love to put question marks in this table. You'll notice it says in a solution that is at least initially 2.0 molar iron thiocyanate. And so what we're going to do is come in here and let's actually include that in our table. Obviously, initially, that's that guy, so we would write our 2.0. Remember, we don't need units necessarily in this table because everything should be in molarity or again partial pressures. We're talking about gases. So now we can start to kind of put some of this together. So case in point, how much of, right, think about it. If this is how much we had initially, then we would assume we have no product. So initially we would say that we have 0 products. So nothing is formed yet. Right? And then what we can do is imagine how much change is going to happen. So if you remember what we talked about in class, the way that we're going to imagine how much would change by, think about the stoichiometry. So we have a 1, a 1, and a 1 in front of each of these compounds. And so if this one goes down by x, then this one has to go stoichiometrically up by x, and this one up by x. So when I write minus x, I'm just saying that there is a certain amount of iron thiocyanate that is making its way, that obviously is going to products, and stoichiometrically, that's how much. So if this goes down by x, this goes by x. This is completely unrelated, but I think it is a good moment to say, let's pretend for a minute your coefficients here were like 2, 1, and 3. Okay, just pretend. So then you would write here, if this one went down by 2x, so whatever number I put here is going to be my coefficient that's in the balanced reaction. So this would be, I would write minus 2x here. Products always go up, so we're going to say plus 1x there, but then plus 3x here. If you do that trick, you'll always get your stoichiometry right. So whatever coefficients I put on these little change x's, so to speak, I should see there. All right, let me get rid of that though, because that's helps. So now we have, so again, like we said, this goes down by x, this goes up by x, and this goes up by x. And then obviously, if you know where you are initially, add together your change, you should get what you're looking for at equilibrium. And so putting all that together, let's actually erase this. So adding downward, 2 plus minus x is just, well, 2 minus x. Then obviously 0 plus x is just x, and 0 plus x is just x. Now, again, our goal is to actually know what these numbers are. Right now we just have them in terms of x, but we were also given our equilibrium constant. So think about it, at equilibrium, these are our equilibrium concentrations, but we know that this is our equilibrium constant itself. So if we put all this together, then what we should be able to determine is this. We're going to go x. Well, here's what I'm saying. So let's put all these together. So guys, obviously at equilibrium, we know what K is. It says that K, which is 8.20 times 10 to the minus 4, that has to be equal to, obviously, our equilibrium expression, right? Which we can now simply say that has to be equal to x times x divided by 2.0 minus x. And so what we have here is a simple equation, a simple algebraic equation that we can solve. Now, you're not going to do algebra because this is not a math course, even though math is heavily evolved. Instead, you have a calculator, and you would be expected to use your calculator here. All right, we're going to go y1, right? y2, and then second trace intersect. Doing that just perfectly, you're going to get a value of x, right, which is 0.040. Right, remember that x is actually a molarity value. It is the concentration. In fact, if we go back into our table, we can see now exactly what we're looking for. So without further ado, we now know that our concentration at equilibrium for iron 3, right, is 0.040. Obviously, the thiocyanate ion's concentration has to be the exact same. And then, of course, the last for us to get our finale here, to get our last one, we are going to get 1.96. So that's how we would do this question. All of these questions are going to be fairly similar. They're not all going to be involving an ice table. Some of these are going to have to combine different reactions to form another reaction like we talked about last week. But just want to go through this example with you guys, just to give you one more opportunity to glean from this as you're going through your homework. So anyway, you guys take care.